Okay. So maybe a quick introduction. So I'm Pieter van Mierlo. I'm a professor at Ghent University at the Biomedical Engineering Department. I'm also CTO and co-founder of Epileptic, which provides quantitative EEG analysis to pharma companies or to clinics. Okay, so the topic of today is EEG source imaging. So what are we measuring with EEG? We'll just try to move this a bit away. All right. So what are we measuring? So Sash already explained you this, that multiple, so more than 100,000 simultaneously active neurons are needed to generate a measurable EEG signals. So it are the pyramidal cells that are the main direct neuronal sources of the EEG signals. And it's actually the excitatory postsynaptic potentials or the inhibitory postsynaptic potentials and not the action potentials that generate the EEG signals. So basically, the EEG is generated from within the gray matter, because in the gray matter, the dendritic trees of the pyramidal neurons line up nicely together, and they generate the signal that we can measure with the EEG electrodes. So there are two types of sources. So imagine you have a brain region that is active. So you have here the gyri, and then here, for instance, the sulci. Here, if the gyri is active, then you generate an electrical field, which has a main maximum or minimum here right on top of this region, which is active. So basically you can see here, if you see the scalp topography, so the scalp topography depicts the electrical activity at all the electrodes at the same time. So most activity is picked up here. So basically, if the source is radial, then you know, okay, the source is coming from this point here underneath the maximal activity. However, if a source is tangential, so we also measure tangential, so the activity of the sulci on EEG. So if the source is tangential, then the electrical field lines goes like this, and basically it creates two maxima. So you have here a maxima and a minima, and the source does not come directly from underneath one of those, but the source is more located in the middle of this. So this is already some rule that you can use to look at the scalp topographies and to know, okay, where is the brain region located that generated this kind of scalp potential map. So what is EEG source imaging? EEG source imaging is actually starting from EEG at a certain time point, and you have a certain scalp topography, and then you actually want to localize where in the brain is this activity coming from. And this is what we call the inverse problem. So inverse problem is, okay, given EEG activity, where in the brain are the sources that cause this brain activity, so the EEG activity. And basically to solve that, you need a forward model. So what is a forward model? Simply put, a forward model is an EEG simulator. So it simulates EEG. So you use a head model that has the geometry of the head, the electrodes, positions, conductivities. You have a source space. So a source space is, okay, where can there be sources that generate potentials that you can measure with EEG electrodes. And then you have a source model, which basically is a dipole or a little battery that you would place inside all of the gray matter regions to then simulate, okay, what does the EEG look like? So basically the source model is the the current dipole. So Seth already hinted this, so that you have when the pyramidal neurons are active, so the dendritic trees are lined up, and they, you can sum the activity over all the pyramidal neurons, and basically their activity is some sort of dipolar pattern. So you have a negative and a positive pole, so you can represent them by a dipole. So with a negative and a positive current, and basically, one dipole represents the electrical activity of a small area of cortex, of a focal source in that cortex, and it has 6 parameters. So the location, so where is it in the brain? Is it somewhere in the temporal lobe? Is it in the occipital lobe? So that's 3 parameters here. Then you also have an orientation. So the pyramidal neurons, they are organized so the dendritic trees are perpendicular to the curvature of the brain. So basically, the orientation, as you saw with the radial and the tangential sources, this really also defines how you have the electrical field at the different electrodes. And then there's one last parameter, the strength or intensity. And this means, how strong is the source? Is it an oscillating source? Or things like this. Okay, so in the forward model, you can include the geometry. So the geometry you can either have from MRI or CT. So in the MRI, you have a very good contrast between soft tissue. So you can see here nicely the white matter, the gray matter. You can also nicely see the scalp. But of course, the problem here is that with MRI, the skull is not very much visualized, so it's difficult to obtain the skull. And basically, in EEG source imaging, the most important structure to model is actually the skull, because it's the least conductive. So the biggest jump in electrical conductivity happens from the CSF to the skull. So basically, this jump and also to the scalp later is the one that you need to model very well to have a good realistic head model. So basically, you can do segmentations of the different tissue types. You can either say, okay, we only use scalp, skull, and brain, or you can go a bit further and say, okay, we use scalp, skull, CSF, and brain. Even some research groups use soft skull, so like the inner bone of the skull, they model as another tissue than the outer skull bone, because the inside of the skull is a bit softer and has a higher conductivity. But basically, starting from the MRI and CT, if available, but usually this is not available in clinical practice, you can make segment all the tissues and make like a geometry model of the head. Then you assign different conductivities, so different electrical conductivities to every tissue. So here is just a table of different publications that all use different conductivity values. So here you can see either you use one for skull, or you can also use one for compact bone and spongy bone. So the spongy bone would be then the bone here inside of the skull. And basically all of these measurements are coming from experiments that were done ex vivo. So basically these values, there's still an uncertainty about these values. There are now coming new techniques also with the MRI, like MR-IET, electrode impedance tomography, that you can try to estimate these conductivity values from the MRI scan. But basically, in the current practice, just the values from literature are used. Then you have your solution space. So basically the solution, so the sources, where are they localized in the brain? So they are in the gray matter, because the dendritic trees of the pyramidal cells are in the gray matter. Either you can model them as just a cortical surface, so you really model the nice bulges of the gyri here at the cortical surface, or you say, okay, they can also occur from within the gray matter, and you can also have an orientation to every point that you estimate. So that's because we know that the pyramidal cells, they have their orientation perpendicular to the cortical surface. So you can basically estimate this, given the segmentation of the gray and the white matter. And then there's also the electrode positions. So as Serge has hinted, there's an electrode system. So basically the 10-20 system, or there's even sub-variants, so the 5-5 system. So every electrode at a certain distance has a certain naming. So the electrodes on the right have an even number, the electrodes on the left have an odd number. And then, of course, the first letter represents the lobe, so the frontal, temporal, central, parietal, occipital. And basically, you can just use this system, so the system that every center is using, and have some landmarks, put these on your models, so this is, for instance, segmented scalp from subjects. You can put like the Nasian, the Inian, and auricular points, and then you can calculate these distances over the head and put these electrodes at the correct distance. Another option is if you have like a Polhemus system, so a digital tracker that you can mark these electrode positions on top of the patient's head, like with this device, or there's also another device, the dome from Maxim, which takes pictures at certain moments and then makes 3D image of where all the electrodes are localized. Okay, so once you have all of this, so you have the segmentation, the conductivities, okay, my sources are in the gray matter, here are my electrode positions, my model I use is a dipole, so I use a negative and a positive. Then you can simulate your EEG. So basically, you say here, this J, this presents the current and the sources in the brain. And then you have the Leadfield matrix, which actually embeds all of this information. So the geometry, the conductivities, where the sources are localized. And then, you can just, by multiplying these, you can get your simulated EEG. And basically, EEG is a sum of multiple sources. So you can estimate the EEG as the sum of a source at a certain location multiplied by the Leadfield at that location, plus the sum of another source at another location multiplied by their Leadfield, and so on. And basically, you can write this in matrix form to say that, okay, the EEG is actually a linear sum of the different sources times the Leadfield calculations. But how do we calculate this Leadfield matrix? So that's the question. But basically, there are several solution methods. There are spherical head models here, as you can see here, that allow you to do an analytical solution of this Leadfield matrix. So based on all the geometry and the electrode positions and conductivities, you can actually have an analytical solution. So they are fast solutions, but then you also have more realistic head models that more incorporate the actual shape of the head, as you have the boundary element model here, which models the the boundary between the tissues. So you model the boundary, for instance, between the brain and the skull, and then you model the boundary between the skull and the scalp, and then the boundary between the scalp and air, so the outside air, which you can see here. And then you also have these more complex models, so the finite element models, in which you use you can use cubes or other tetrahedric voxels, which you assign to a certain tissue class, which you then assign a certain conductivity to, and this allows more detailed mapping of the head, so more detailed calculation of what the potentials would be like if you would have a source here in the gray matter. What would the potentials be if you map the complete head like this? Okay, so then we have our forward model. So we basically, what is a forward model? So we have this Leadfield matrix that says, okay, so the Leadfield matrix basically gives you the translation between a source and a brain and how you measure it at the scalp. And with this Leadfield matrix, we can then solve the inverse problem. Basically, what you try to do is you have this, so the Leadfield matrix is fixed. It's dependent on the model you use, on the forward model. And then you can alter the sources in the brain, so this J, you can alter this, and then you can try to find the J that leads to a minimization of the measured EEG minus the simulated EEG. And that's actually how you can solve the inverse problem. So basically, you use your EEG generator, you generate EEG data, you have the measured EEG data, you have the residuals, and then you can make a cost function out of that, and you can use inverse techniques to optimize that cost function. There's two important inverse solution techniques. So one is the equivalent current dipole, where the EEG signals are assumed to be generated by a relatively small number of focal sources. So basically here you say, okay, the EEG must come for instance, from one source in the brain, and then you estimate, okay, what is the source that gives me, that generates the EEG that comes closest to the measured EEG. So that's one solution method. Another solution method is the distributed dipoles approach, where all possible source locations are considered simultaneously. So instead of saying, okay, I need some sources that are active in the brain, you say, no, every brain region can be active. They are just active with a different amplitude, let's say. And you estimate the amplitude, so the activity of all the brain regions, so of all the dipoles, so which are usually around 10,000, 5,000, 10,000 at once. So here you see, if you would use an equivalent current dipole, so if you would say, okay, we use a dipole at one time point, then you have your measured EEG, and basically you have a 60 problem in which you have all the dipoles in the brain, so all the sources in the brain that you can change their position, orientation, and intensity, and you look for the source that minimizes this residual relative energy. So basically you try all these different parameters, and then you say, okay, source at position X, Y, Z with orientation theta and phi and intensity I gives you the best solution. So this is the source that generates the EEG. So with the for instance, here an example of that. So we have epileptic spikes here. So you see here a phase reversal of the epileptic spikes over F8. So this is the spike, this is the map. And then you can say, okay, we localize this map with dipoles, and you say, okay, they come from this region in the brain. And here, another example, here we have a spike with maximum over F4. And here you can see that it localizes a bit more dispersed in the brain. But this dipole technique can be used to estimate like a bipolar field, or a nice smooth field that is probably caused by one single source. For the distributed EEG source imaging, basically you look for some sources in the brain that maximize the data fit, but you also add some regularization. So you add some function on the sources that you say, okay, I want, for instance, with the minimum norm solution, I want sources that have a very good data fit, but I also want the sources that produce the minimal amount of energy. So here, so the constraint of the minimum norm solution is the current distribution over all solution points as minimum energy. And of course, that also the forward solution of this distribution optimally explains the measured data, so that's the data fit. But the regularization is that you have least energy over your solution space. And when you impose that constraint, then this is the solution. You don't need to mind the formulas, but basically based on the lead fields, you can, and the noise that is in the data, you can have a solution that gives you a unique solution here. But the disadvantage of minimum norm solutions, because you state here, so as minimum energy. So basically, if you say I want a solution that has minimal energy, you will actually bias your solutions towards superficial sources because they are closer to the sensors and they need less amplitude to achieve the same electrical field as deeper sources. So basically here the constraint, because you have this imposed constraint, the solutions will be more shifted towards the neocortex and less to the deeper brain regions. So there's a solution for that. So you can have a weighted minimum norm solution in which you introduce a weighting matrix, and the weighting matrix actually gets rid of this bias. So basically in the weighting matrix, there's some kind of Leadfield normalization happening, so that every source has the same probability of having generating the measured EEG. And then you have other solutions like the LORETA family of solutions. And basically here so the norm of the second order spatial derivative of the current source distribution is minimized. So that's how they do it. But what do they want to do it? They want to ensure spatial coherence and smoothness. So they say, okay, your sources here, they need to have spatially need to be very, very smooth, because one region is active, then the region a bit next to it also needs to have some of this activity. It cannot be like opposite activity. So that's the LORETA family. And you will work with also these LORETA, think with eLORETA during the technical session later. Okay, so then now we have these source imaging methods. So what can you do with them? So you can, for instance, if you have an ERP, so an event-related potential of a right hand movement, then you can say, okay, I want a distributed solution. Here it's a LORETA solution, and then you can see, okay, that the right hand movement comes from here So at time point 0 here, it's estimated here in the brain. So you can basically localize the activity of the event-related potentials at the different stages of the potential. So here you can see another visual evoked potential of phase presentation. So phases are presented to the subject. And then here you first see the visual stimulus, and then later you see the perception of the phase. And this perception of the phase, then you can localize here also with the distributed model. And here you can see that the mesial temporal lobe, but also the fusiform gyrus is active, which has been linked to phase recognition. And then there's also the automated source localization. So with Epilogue, we do automated source localization. So we get from the centers, so the epilepsy centers, we get EEG data of several days, can be up to 7 days. We detect the spikes. So here you can see 4 clusters of spikes that we detect. So for instance, we detect spikes over T8, so we have 366. It's only 2 days of recordings here. And you can see that during night, there's usually more epileptic spikes that are recorded. So when the patient sleeps. So here you can see the different clusters, also the lateralization. And then you can see the localization. So here you can already see that the patient has a brain lesion, and we localize this activity. So here we use LORETA, so one of the LORETA families that ensures you a spatial smooth solution. As you can see here by the color map, that's spatially very smooth. So it localizes here in this brain region at the peak of the spike. And here we also localize 100 single spikes that mostly look like average spike, and they localize here in the same region, indicating to the clinician that potentially this region is causing the epileptic seizures. So here is the irritative zone, so the epileptic interictal spikes that are localized, but this is a piece of the puzzle that is given to the clinician to see whether they can treat the patients with operation or with neuromodulation. And for this, we use a patient-specific head model, and we can also, with the more fancy methods like the finite element methods, you can also model these lesions, as you can see here. So it's really modeled as CSF inside the head, so that you have the exact patient structural information that is taken into account. There's many actually now academic software packages or commercial software packages that are available to do EEG source imaging. Here is a list. So I copied this table from one of the publications of Christophe Michel and Denis Brunet, who recently wrote a review about EEG source localization with the different steps, and also gives a nice overview of which packages are available. So please take a look at that publication if you want to look what the advantages of using one of the other. They all have different inverse models. Most have dipole modeling. Some also have LORETA. And then there's also the commercial software packages that you can buy to also do this source imaging. So in summary, EEG source imaging needs a forward model and an inverse solution technique. So the forward model you can make very complicated or as easy as you want. So you can make a spherical head model, which is easy, or a more realistic head model that contains the head geometry, tissue conductivity, electrode positions, and of course the solution space, so the gray matter. So the inverse technique optimizes the source space solutions by imposing some constraints And it's actually those constraints that lead to a unique solution. So that gives you then, one solution of sources that cause your measured EEG. And EEG source localization or EEG source imaging, it's very useful to localize ERPs. Basically, because EEG has a millisecond temporal resolution. We even have amplifiers now that record at a microsecond. So basically, that allows you to look at these brain responses to certain events with a millisecond scale, and you can also localize them inside the brain with this millisecond scale. And of course, for epileptic seizures and epileptic spikes, but also for epileptic seizures, it's very good to localize where the activity comes from, so you can help treat the patient. Okay, so that was the presentation. So I thank you for your attention. And are there any questions?